differential equation, dy dt equals y times t. Is the equation separable? Yes. What makes an equation separable? Multiplication and division, which is the same thing as multiplication, right? If the two variables are only separated by multiplication. Okay, so yes. And is the equation autonomous? No. What makes an equation autonomous? Yeah, the right-hand side can only have one variable in it, and that variable has to be the dependent variable, which in this case is y. Good. So for this to be autonomous, you could only have y's on the right-hand side of that differential equation. Does that equation represent an initial value problem? No, because I gave you no initial condition, right? An initial value problem is a differential equation plus some other piece of information like the value of y at some x or some t value. Okay, so just a reminder, your quiz grade for the day, your reading quiz grade for the day is out of 4 points. 1 point for each correct answer on the quiz, 1 point for writing the question and handing it in, and 1 point for taking notes can make up for a question that you got wrong if you took notes. And please record the score on that quiz next to the date on the folder under your name. Okay, so today we're going to learn an analytic technique for solving one small special kind of differential equation called a separable differential equation. So just like when you first started learning algebra and you first started to learn what an equation was, in our first 2 classes we were able to take a potential solution and check it. Like, does this thing work? If you plug it into the equation, does it actually make the equation true? And now we're going to learn one of the really basic techniques for solving a differential equation, for finding the solution analytically. However, just like you can study algebra, you could study algebra for 3 years and not learn every technique for solving the different kinds of equations that pop up. Because you got linear, you got quadratic, you got polynomial, you got absolute value, you got square roots, you got rational exponents. I could go on and on, right? There's so many different kinds of equations, and there's a different technique for each one. Same thing with differential equations. There's so many different classifications of differential equations, and there's a different technique for each one. So today we're going to learn the first and the one that relies most on things we already know. All right, so to solve a separable equation, and a separable equation means it can be written as some stuff with t's times some stuff with y's. Right? Stuff with t's times stuff with y's. So it might not be given to you that way, but if you can make it that way, then you can solve it by separation of variables. So to solve a separable equation, you treat the dy dt like a fraction, and you gather all the y's on one side and all the t's on the other. So here I'm just going to like cross multiply. So I would have y squared dy is equal to t dt. Multiplying both sides of that equation by y squared and both sides of that equation by dt. So now I have all my y's on one side and all my t's on the other, and I can integrate both sides, right? If I put an integral symbol in the front of that, that makes sense. I can evaluate the integral of y squared dy. That's something we know how to do. And as long as you do the same thing to both sides, the equation's still true. And I can integrate t dt, integrate t with respect to t. That's something we know how to do. Okay, so what is the antiderivative of y squared? Y cubed over 3. So I've got y cubed over 3 plus c, right, my constant. And antiderivative of t squared over 2 plus a constant, but it's not necessarily the same constant as the one over here. So I could call it like, I don't know, K, whatever, or C sub 2. So now if I was going to solve this equation for y, my first thing I would do is I would subtract c from both sides, right? I'd get that constant to the other side. And I'll have y cubed over 3. Yeah, let's call this c1 and we'll call this c2. Changing my mind. Just names for constants. I'm going to subtract c1 from both sides. So I have t squared over 2. And then I have c2 minus c1. But because c2 represents an arbitrary constant, it can take on any possible value, c2 or c1. When I subtract them, I just get another arbitrary constant, right? It's just completely random, can take on any value. So I'm just going to call that thing c3, some other constant. I'm not going to keep track of it's really c2 minus c1. I don't care. It's just some constant. And then to finish solving this thing for y, I'd multiply both sides by 3. So I have y cubed is equal to 3t squared over 2, or 3 halves t squared. And my constant is now 3 times c3. But again, c3 is totally arbitrary. Tripling it just gives you another different arbitrary number. So I could call that thing c4, another constant. Because I just don't care what it is very much because it can take on every single possible value. And then finally, cube root both sides. And I've got a function y of t, y with respect to t, is the cube root of 3 halves t squared plus some arbitrary constant. And you could call that thing c4, you could leave it c4, you could call it c5. I usually, as a convention, which is completely my particular choice, when I write my final answer, I call my one final constant that I kept c, no subscript. Yep. You can't, because you can't take, if you have the square root of a sum, you can't take the square root of the two pieces separately. Like, yeah, that's fine. Yeah. Yeah, which that's totally fine. Last time I taught this, people were like rioting that I was leaving off the C's and what are you doing? So anyways, I was just trying to be really explicit the first couple times, so you can see where the C's are going and what they're doing. But really, they're arbitrary, and you can just kind of lump all of your C's together into one arbitrary C. And you can do it in your head if you want. You don't have to write them all out like that. So that's separation of variables. Not so bad, right? You have to be able to get the t's on one side and the y's on the other. You have to be able to separate them to different sides. And then you have to remember how to integrate things, which is why I had you do a little bit of review of some integration techniques last couple of classes. I can't see. Yeah, we're not gonna be able to avoid things. There's a lot of integration in this class. Yeah, we're not gonna be able to get out of it. Okay, so next we're gonna do a mixing problem, and my picture didn't copy well. Let me just fix that. Okay, so this is these mixture problems are like classic differential equations modeling. We're given a lot of information about some rates, and we're going to try to set up a model for the amount of sugar in this vat of sugar water. Okay. So we've got this large vat that contains sugar water. It's going to be used to be made into soft drinks. So the vat contains 100 gallons of liquid. And the amount flowing in is the exact same as the amount flowing out. So there's always going to be 100 gallons in the vat. And we're going to assume that it's kept well mixed so that the concentration of sugar is uniform throughout. It's not going to settle to the bottom. And then we have these 3 bullets that gives us the real information about how much sugar, right? Sugar water that contains 5 tablespoons of sugar per gallon enters the vat through pipe A at a rate of 2 gallons per minute. So they've given us 2 pieces of information, 5 tablespoons of sugar per gallon and 2 gallons per minute. So 2 different rates there. And then sugar water that contains 10 tablespoons of sugar per gallon enters the vat at 1 gallon per minute from pipe B. And then pipe C drains sugar water that's been all mixed up in there. So we don't actually know how much sugar is in there because sugar is entering through the 2 pipes A and B. And it's leaving through pipe C at 3 gallons per minute. And what we're going to try to do is write a model for S, which is going to represent the total amount of sugar in the vat, which is changing with respect to time. Okay, so we had some initial amount of sugar in there, and then we have some sugar water entering and the mixture leaving. All right, so remember S is a function of time. It's changing with time, and it's going to represent the number of tablespoons of sugar in the vat, right, at any given time t. And I'm going to write my model as a differential equation because everything I'm given is rates. So it makes sense to write this as a model for how the amount of sugar is changing with respect to time. Okay, so as a sort of overarching simplification of the model, the rate at which sugar is changing in the vat, you can break it down to the rate at which sugar is entering minus the rate at which sugar is leaving, right? So you have to figure out how fast is sugar coming in and how fast is sugar going out. The difference between the two tells you how fast the amount of sugar is changing in the vat. All right, so let's look at the rate in via pipe A. So what? Oh, the units are definitely going to matter. Yeah. So if I'm looking for ds dt, what should the units on ds dt be? Tablespoons per minute. Yeah, because S is being measured in tablespoons of sugar. T is being measured in minutes. So ds dt, we should be measuring in tablespoons per minute, right? The numerator units over the denominator units. So I need in tablespoons per minute the rate in via pipe A. Okay, so they didn't give us that. They gave us tablespoons per gallon and gallons per minute. Can I somehow, yeah, what do I do? No, we can use gallons. We don't have to convert to liters. Oh, sorry, that was pipe B. Sorry. Here's A, B, C. They are both 10 per minute. You're right. So for A, if we do a little unit analysis, we can say 5 tablespoons per gallon. And if you multiply by 2 gallons per minute, right, then the gallons cancel, and you end up with 10 tablespoons per minute. So we know how fast sugar is going in through pipe A, and sugar going out through pipe C, in through pipe B. You do the same thing. 10 tablespoons per gallon times 1 gallon per minute. It's going to also give you 10 tablespoons per minute. 10 tablespoons per gallon times 1 gallon per minute. Gallons cancel. So we get 10 tablespoons per minute flowing in through pipe B. So if you add the two rates, A and B, how fast is sugar entering the vat? 20 tablespoons per minute. Okay, so I'm going to add that to my differential equation. Okay, then I have to figure out how fast it's leaving via pipe C. So I'm trying to measure this in tablespoons per minute. See, maybe I'll do my side work for rate out over here. Rate out via C. So pipe C, they only gave me a gallons per minute, right? So because we don't know how much sugar is in there, right? So the mixture is leaving at 3 gallons per minute. So if I try to kind of copy the model I did for the rate in, I need something tablespoons per gallon times 3 gallons per minute. My gallons will cancel, and I'll end up with something in tablespoons per minute. Can you explain how you got that? Perfect. So this first fraction here, we're looking at how much sugar is in the vat. We want to know how many tablespoons per gallon are in this whole vat. And in order to calculate that, I need to know how much sugar is in there, which we are measuring with the letter S. Make sure you can differentiate that from a 5. I confused myself like 17 times when I was solving this problem. And in the vat, there are 100 gallons, right? There's S tablespoons of sugar, 100 gallons of mixture. And so when I simplify that, I end up with 3 S tablespoons per minute, over 100 tablespoons per minute. So that becomes my rate out part of the differential equation. And if you were so inclined, you could combine these into a single fraction. It does not matter. This becomes 2000 minus 3S over 100 tablespoons per minute. Okay. So the hard part of this equation, of this problem, is writing the differential equation. Analyzing the solutions to the differential equation, we can do via some analytic techniques. Yes. No, that's a 20. That's definitely a 20. But when I combined these two fractions, I added them together. So I had to get a common denominator. All right, so I'm going to let you do some practice. You're going to deal with some things about this differential equation, and you're going to do some practice solving by separation of variables.